Niels Bohr came up with a model for a hydrogen atom based on the emission spectrum of hydrogen. When energy is provided to a hydrogen gas, there were certain wavelengths of light that were emitted. And observing that and studying that, he came up with his model of the atom. Now, some of these things that Bohr said we now know are not strictly true. However, they're still used because they do accurately determine some averages of what happens and also determine the energy levels. So these were a few assumptions of Bohr's model. One was that electrons orbit the nucleus on circular paths, which we now know not to be entirely strictly true. He was still thinking of these electrons in the classical definition of particles, but he said that electrons orbit the nucleus on circular paths. He said that only certain orbits are allowed, which fits in with the idea of energy quantization. And then the third thing he said was that electrons emit or absorb, forgot his S, absorb electromagnetic radiation to move from one energy level to another. Okay. He using the idea that centripetal force applied on the electron is caused by the electric force. The allowed orbits from hydrogen, he derived the allowed orbits for hydrogen. That's on page 1084 in your book if you want to see the derivation. I'm just going to give you the result. And the result is this, that R sub n, where n is any integer, as it often has been, is h squared over 4 pi squared mk e squared times n squared. This is the mass of the electron. K is our constant from electromagnetism. E is the electron charge, and h is Planck's constant. So this here is kind of an ugly expression, but it is all just one constant. And then n can be 1, 2, 3. So if you plug in n equals 1, you get one of the Bohr radius. You get a Bohr radius, it's called. If you plug in n equals 2, you get the next one, and so forth. Following along again from the idea of centripetal force, the velocity of an electron in the nth orbit, so it's 2 pi k e squared over h n, where again n equals 1, 2, 3, etc. Okay, so these are the allowed orbits. The energy then of these allowed orbits. Now energy is kinetic energy plus potential energy, and we know that kinetic energy is half mv squared, and we know electric potential energy is minus k q1 q2 over r. So we can start filling in values for this. Now we're dealing with electric force. So we know that centripetal force is mv squared over r, and if that centripetal force is provided by the electric force, then, well, that's k q1, which is the electron, q2, which is the nucleus. And Bohr did this for hydrogen, but it also generalizes to other molecules. So the nucleus has a charge of the atomic number Z times the electron charge. K q1 q2 over r squared. Well, so that gives us that mv squared equals this. So then our energy becomes half k z e squared over r. Meanwhile, this k q1 q2 is minus, well, k q1 times q2 we've already established is this z e squared over r. And these are the same thing, just with a factor of 2, so the energy is minus k z e squared over 2r. And if we plug in our expression for r sub n here, we get that the energy at a given radius is minus 2 pi squared mass of the electron k squared e to the fourth over h squared times z squared over n squared. And I pull this out separately because this is all just a constant, and when you multiply it out, it comes out to minus 13.6 electron volts times z squared over n squared, which is pretty simple, even though this looks kind of nasty. You just take 13.6 times the atomic number over the number of the radius number, I guess you could call it. Yeah, so now notice that as this is a 1 over n squared, but notice that as n increases then, we're getting closer to 0, which means our energy is increasing. This is tying in with the idea from electrical energy that our energy equals 0 at infinity. And so as we get up to the bajillionth energy level, this energy is going to 0, right? Which makes sense because our radius is getting larger and larger. But it is getting closer and closer to 0. So even though n can keep increasing without bound, this energy does have an asymptote at 0. You can't get more energy than 0 electron volts in a Bohr radius, right? Or in the Bohr model of the atom. Now, radiation, as Bohr said, occurs when we move between energy levels. So let's say, for example, we go from the third energy level to the first. An electron absorbs some energy somehow, it gets excited up to the third energy level, and then it goes down to the first, and it does so. This energy then is given off in the form of a photon. So what happens is that our energy, the change in energy of our electron, we start off in the third, go to the first, so we've got a minus 13.6, but we're starting, let's say we're in a hydrogen atom. So Z equals 1, and we're going, our final energy level is the first, so that gives us a 1 over 1 squared, and our initial energy level is the third, that's 1 over 3 squared. And if we plug those numbers in, we get minus 12.08 repeating electron volts, which converted is 1.9342 times 10 to the minus 18th joules. So this is how much energy, the energy change of the electron, and so this energy has to go somewhere. So if the electron is losing this much energy, that means that there's a photon floating around that has 1.9342 times 10 to the minus 18th joules of energy in the form of a photon. And we can plug in those numbers and get a frequency of 2.917, etc., times 10 to the 15th hertz, which, as it turns out, is a UV ray. Now, if we do the same math from the third energy level to the second, then you wind up getting, you just run through the same math, you get a wavelength of 4.558 times 10 to the 14th hertz, which is 658 nanometers, which is an orange, like kind of a red-orange color. And this is one of the lines that you can see. We have these things called a spectroscope, and what they typically have is they have tubes full of an ionized gas of a particular atom. If we're looking at this, it would be hydrogen. And if you run a current through that, then the electrons will get excited and then emit radiation as they go back down to their lower energy levels. And there are different lines that you see, and I think there are 3 or 4 of them that are in the visible spectrum. But just doing the math, in the transitions between the various energy levels can let you figure out what those are. Anything going down to the first energy level is beyond the range of human vision, but several of the ones that terminate in n equals 2 are visible, and you can. It's really simple to actually. It's in the couple of sections before this one in the book, where it does talk about what the spectrum for hydrogen is. So in general, like if you're given an equation if you're given this, you have these equations for energy levels, you can find the wavelength of something that's a wavelength of a photon emitted by following through this process. Now this applies to atoms that are hydrogen-like, meaning it applies to relatively small atoms. Once you get to larger atoms, there's an effect that you may have heard of from chemistry called electron shielding. And so the force on an electron in an outer energy level from the nucleus is kind of shielded by the electrons that are closer into the nucleus. And so this doesn't quite apply because we derived this using that the electric force was just that electron, just the nucleus was related to the nucleus charge times the electron charge. So this only works for atoms up to a particular size, but it works very well for those smaller atoms.